Okay, so let's talk about our actual electron configurations. I'm going to draw a really simple one for you, one of the simplest ones that we could do. And then we're going to talk about the 3 rules that go along with that. And then we're going to do slightly more complicated ones as examples later on in the next video so that you can see how those rules are actually going to play out in a bigger setting. So we're going to start with one that's relatively simple. And again, you need to have your periodic table out because obviously I've miniaturized mine and I don't have the whole thing here. So we're going to start with nitrogen. Okay, and if we went out and we found our little chart for nitrogen, we would see that nitrogen had an atomic number of 7. And it's got a molar mass, an atomic weight of something like 14.01 or 14.001 or something like that. So 7 is what's important to us because that's the number of electrons that we have. Remember that 7 is actually the number of protons, but in a neutral atom, it's going to have an equal number of electrons to balance it out. And so I'm going to draw my electron configuration for nitrogen, and then I'm going to use the model that I've drawn here to explain the rules to you. The way that we're drawing this is what would be alternatively called either longhand electron configurations, or oftentimes you would hear it called orbital notation instead of longhand electron configuration. So what these little boxes are here, and sometimes you'll see them drawn, if you'll see them drawn in a book, a textbook or something like that, they would actually be drawn out as little boxes like that. That's not really practical for us when you're writing a whole lot of them, so usually we're just going to draw dashed lines. Each one of those lines represents an orbital. Okay, and remember, an orbital is a region in space where we have a good probability of finding a given electron. And so I know that I have 7 electrons here, and so I'm going to put my 7 electrons in such a fashion to draw the correct orbital notation of our nitrogen. So all of the pink arrows there are electrons, and you'll see that I have 7 of them. And I've sort of arranged them in a certain way, and I sort of started to draw the path in a certain way. And so I'm going to give you the rules that I use to do that, and then in the next video we'll work a couple more examples so you can see a little bit more about how to draw them out in this way. And by the way, we don't usually draw them out in this way. You'll see them a couple of times this way, but most of the time we draw them in a much more condensed fashion. We'll get to that probably in our 3rd video here. So what are the rules that we're going to use for this? Well, rule number 1 is called the Aufbau principle. Okay? The Aufbau principle, there's always these really important, complicated scientific definitions for them, and I'll pop those up in the video for you. But what the Aufbau principle really says, when it boils down to like simple normal person speak, is start at the bottom. Okay? Remember that if we were drawing this in some sort of like Bohr model structure here, that this would be energy level 1 and this would be energy level 2, and there's a nucleus here. And so you want to start filling your electrons closest to the nucleus. The lowest energy electrons are going to be closest to the nucleus. And what the Aufbau principle then tells us is start from the bottom. So when I started putting my electrons in here, I started at the 1s, I went to 2s, and then I went to 2p, and then I would go to 3s and 3p and so on and so forth, like we'll do in the next part of the video. So the Aufbau principle says start at the bottom. And again, I'll pop up the more complicated definition for you, but really that's essentially what it comes down to. I mean, it says, hey, you want to start at the lowest energy levels and go to the higher ones. For us, it means start at the bottom. What that also means is that when you're drawing these out, and this is going to be tough for some of you, don't start with 1s at the top and go that way. Start with 1s at the bottom and go the other way. That just tends to be the way they're drawn. Sometimes an alternative method would also be that we could have drawn them out and said 1s, 2s. We would have drawn them in a straight line left to right because that's the way we would normally read things. And that way can be useful. That's actually pretty close to what we're going to do in shorthand here in a little bit. But this is traditional orbital notation because this sort of really lets you know that this is lowest, next lowest, highest energy level for this particular atom, and that's important. Okay, so rule number 2 is the Pauli exclusion principle. That sounds really complicated. The actual, again, the complicated scientific definition of it is a lot more complicated. Basically, the Pauli exclusion principle says, hey, every electron has a unique set of 4 quantum numbers, and no 2 electrons in the same atom can have the same 4 quantum numbers. What that would mean is that there always has to be a spin to them. And you're like, whoa, what does all that mean? It doesn't really matter that much for us at the moment. What that means for us in terms of actually writing our electron configurations, again, the easy speak or the normal person speak would be, the Pauli exclusion principle tells us that you can only fit 2 electrons in an orbital. And that when you put 2 electrons in the orbital, the first one always goes up and the second one always goes down. That means that they can't have the same spin. Electrons are spinning, and so we're saying this way that one's spinning this way, the other one's spinning the other way. Okay? And again, we're not getting into all the quantum mechanics of that, but that's essentially what the Pauli exclusion principle tells us at our level that we're worried about, which is I can only fit 2 electrons in each of the orbitals that I'm going to set up. Okay, so that's rule number 2. Rule number 3 is Hhunds rule, and what Hhunds rule tells us is that if we have orbitals that are on the same energy level, so remember that I said that alpha principle says that we start at the bottom, lowest energy, so 1s is at an energy level, and then 2s is at a different energy level, and 2p is higher than that. But within 2p, we have 3 orbitals, okay, that are all at the exact same energy level. Okay, those have a specific name. We call those degenerate orbitals, meaning that they're all orbitals at the same energy. And what Hhunds rule says is that if you're putting electrons into degenerate orbitals, that what would be most favorable is that if you maximize the number of electrons with the same spin. And you're like, again, what? What does that mean? That's sort of the more complicated definition. What Hhunds rule really says for us is that when you're putting electrons into degenerate or the same level boxes, that you put 1 in each before you go back and put the second electron in any of the boxes. So the Pauli exclusion principle tells me I can't put more than 2 in a box, but Hhunds rule tells me that sometimes I put 1 in each box before I then go back and put the second one in. So this is a nitrogen. If we had an oxygen, and let me write that up there, that this is nitrogen. If we had an oxygen, say, and I had an 8th electron, remember oxygen is the next element over from nitrogen, we had an 8th electron, then I would go back in and I would have done my Hhunds rule, and then I would come back and fill in my 8th electron there, and then fluorine would be 9, and neon would be 10, and so on and so forth. Okay? So, one more quick thing, because you might have been saying, okay, that's great, I understand what you're saying about degenerate orbitals being those in the same level. Why does S have 1 and P has 3, how many did D and F have? So real quick, just let me tell you what each of those things are, just to make sure that everybody's okay with that. So they work like this, S, P, D, F. Okay, S always has 1 orbital, P always has 3, D always has 5. Guess what F has? 7. If we went to a G or an H, which again are theoretically possible, then we would have 9 and 11 and so on and so forth. And again, there's a quantum number reason behind that that is really deeper than we need to go right now. But what's important to us is this tells us how many boxes each of these get. Now here's the beauty of this. You could memorize this and that will work just fine, but the periodic table itself actually leads you to all of that stuff. If you look at the periodic table and what I said was the S block before, there are two columns there, which means that I can only fit 2 electrons. Okay, each column is an electron. And so if I can only fit 2 electrons, that means I only need 1 orbital because each orbital holds 2 electrons. If I go over to the P, there are 6 columns there. Okay, and look at your periodic table right now. There's 6 columns there. 6 columns, 6 electrons means that I need 3 orbitals to hold that. D has 10, F has 14 most of the time. You're like, most of the time, what does that mean? Well, on some periodic tables, they'll take, since the F block goes right here, they'll pull that down and they'll sort of put the D1 there, and we're not going to worry about that at the moment. But again, you could just look at the periodic table to be able to figure out how many boxes, and by boxes, of course, I mean orbitals, go in each one of them. Okay, so that's the basics. We're going to work some more complicated ones in the next video, and then we'll talk about how to condense this down to a smaller version in the video after that. Thanks, kiddos.